Good morning, students. Our today's topic is arithmetic logic shift unit. And this is the last unit in this chapter. Okay, we are learning about register transfer and micro operations. And in this chapter, we have learned about register transfer language, right? The register transfer language that uses symbolic notations to describe the micro operation that transfers information among registers. And then we learned about register transfer. Okay, the second topic, register transfer. It is transferring information between registers. Correct? If I write R2, yes, this means, okay, transfer the content of register R1 to R2. Okay, so this is the micro operation for transferring the content of register. And conditional transfer occurs when a control condition is given. Okay, like if I say P R2, okay, R1. So when I write this operation, this means transfer the content of R1 to register R2 under this condition. Okay, here P is a control variable that controls the operation. Okay, this micro operation of register transfer. So depending on the value of P, when the value of P is 1, this happens. Okay, this operation is done. So this is the conditional transfer. Okay, the value of this P controls the operation. And here for this transfer, okay, transfer between register to happen, what we need is, we need bus lines, right? Okay, for taking the content of register R1 and load it into R2. Okay, so for that we need bus lines, and we also learned about this bus and memory transfers. Okay, the common bus system. We have seen the construction of the common bus system. Okay, that is used to carry the content of registers, information, content of register to another register. So the bus system, construction of bus system is done with multiplexers, correct? Multiplexer is a combinational circuit that receives information from many inputs and directs it to a single output. Okay, so these multiplexers are used, and here the number of multiplexers used depends on the number of bits in the register. Okay, so here we have seen this already, construction of common bus system using these multiplexers. There are 4 registers and each with 4 bits. So all these 4 bits of each register are connected to the multiplexer. Okay, these bits are the input to the multiplexer. And the multiplexer will select one bit out of these 4 bits, okay, and direct it to output to the bus lines, okay, based on the value of S0 and S1. Not is 0, okay, the value 0, 0, select the input 0 of multiplexer, okay, this particular input. So when 0 is selected, what all the inputs connected to this 0th input? Okay, the register connected to this is A0, A1, A2, and A3. So register A gets selected. The bits of register A will be placed in the bus for transferring and being taken to the destination register. When the value of S0 and S1 and S0 are 0 and 1, the 1 bit of the multiplexer is selected. That is, okay, the bits connected to this 1 bit of the bit 1 of this multiplexer is input 1 of this multiplexer is B. Okay, so B0, B1, B2, and B3. So these content will be placed on the register and taken to the destination register or loaded into the destination register. And when the value of this S1 and S0 are 1 and 0, okay, multiplexer input 2 get selected, and that get directed to the bus, okay, as an output, as the output. If you see the input 2, okay, multiplexer input 2, the bits connected are the bits of register C, C0, C1, C2, and C3. So the content of register C will be placed on the common bus. Okay, the common bus carries the content of C to the destination register. And if the input is 1, if the selection input, okay, S0 and S1 are 1 and 1, the multiplexer input gets selected as 3, okay, and that get directed, and 3 is register D. Register D is connected to the multiplexer input 3. So the content of register D will be transferred, okay, to the destination register. So this way we can have a common bus lines, okay, common bus system that can carry information from different registers, source registers to destination registers. So when we write the operation R1, okay, this means transferring the content of R1 to R2, but it is placing first operation. Okay, there are two operations involved in this. One is placing the content of R1 in the bus. Okay, this process is called selection. Out of these 4 registers, A, B, C, and D, okay, one register is selected by the multiplexer, okay, by activating the input 0, the register A, or by activating input 1, register B. Okay, this way one register gets selected at a time. Okay, so placing the content of register on the bus line, that is selection. So this is one process. Okay, the first step of this transfer operation. And the second step is loading the content of bus into the destination register R2. Correct? Our destination register is R2. Okay, first operation is placing the content of the source register R1 onto the bus. Okay, so this is selection, selecting the register and placing the content of the register on the bus. And then the second operation is loading the content, okay, that is placed on the bus into the destination register. Okay, so this operation is loading, okay, loading the register R2. Okay, so this register transfer is done by using this command line. Okay, so we have discussed this. Okay, and here we also we have seen the another way of constructing the common bus system is using 3-state buffers. Okay, here we used multiplexers, and the same can be constructed using 3-state buffers. 3-state buffers is a buffer usually have 2 states, 0 or 1. That depends on the input of the buffer. Okay, input given to the buffer. If the input is 0, the output state will be 0. If the input to the buffer is 1, the output will be 1. But here this 3-state buffers will have 3 states. The third state is the high impedance state. Okay, that we call this is disconnected. Okay, there is no connection here between input and output, so there will not be any output. Okay, so we say that the buffer, here it is a disabled state or disconnected state. Okay, it is high impedance state. So these 3-state buffers can be used to construct the common bus system. Okay, that we have seen that bit A0, B0, C0, and D0. Okay, the least significant 4 bits of the 4 registers are taken here. Okay, this is this part of the the circuit. So here using this 3-state buffers, okay, what we can do is we can information from one register can be selected and directed to the bus line, okay, by disabling all the other buffers and enabling only one buffer at a time. Okay, so here we yes, the control line. Okay, this is the control line to the buffer. Okay, the state of the buffer can be controlled by using this control line. Okay, if the control line is 1, we have seen this. If the control line is 1, the output of the buffer will be the, no, it will, yes, the state will be one of the states, 0 or 1. Okay, if it is 0, if the C, value of C, the control input is 0, the state buffer goes to the high impedance state. Okay, so by setting this value of C, okay, by changing the value of C, we can enable one buffer at a time so that content of one register will be placed on the bus. Okay, so that is done by the control of this C, okay, is done by the decoder circuit. Okay, this is for one particular bit one least significant bit. And for constructing for all the bits, we need 4 like this. Okay, we need 4 circuit of the same. So we discussed about this bus and memory transfers. Okay, and even to transfer the content of memory to register or from register to memory. Okay, for performing read and write operations. Okay, we use this bus lines. And then we discussed about arithmetic micro operations such as performing addition, subtraction. Okay, and for subtraction, complementation. Okay, finding the complement of the subtrahend, and then increment and decrement. All these arithmetic operations, micro operations, can be done by this arithmetic circuit, correct? And logic operations. Logic operations are the the basic logic operations we discussed, and or, XOR, not. Okay, all these can be done. Okay, one of the operations, the circuit for logic, yes, here is the logic circuit. Okay, that allows this multiplexer chooses one of the operation and direct it as output. So one of the operation, logic operation, will be performed. And we also have discussed in the last class, in yesterday's class, we discussed about shift micro operations. Only 2 micro operations. Okay, on shift is performed. One is shifting the content of the register to right and shifting to left. Okay, we discussed about the 3 types of shift: logical shift, circular shift, and arithmetic shifts. Okay, and here let's learn about this arithmetic logic shift unit. Okay, the arithmetic operations, what we have learned, okay, micro operations, logic micro operations, okay, can and the shift of micro operations, okay, that we have learned earlier, can be combined, okay, here into one ALU, arithmetic and logic unit. Okay, the shift micro operations are often performed in a separate circuit, okay, separate unit, but sometimes it is combined with ALU. Okay, so we call it, okay, as arithmetic logic and shift unit. Okay, when the arithmetic and logic unit performs shift operation, when the circuit for performing shift operation is included with this ALU, okay, we call it as arithmetic logic and shift unit. Okay, so now you have understood how we will discuss it more. Instead of having individual registers performing the micro operations directly, computer system employ a number of storage registers connected to a common operational unit, okay, called arithmetic and logic unit. So what is arithmetic and logic unit? It is the common operational unit that performs all the arithmetic, logic, and shift micro operations, okay, in a single circuit. Okay, so this is the hardware implementation of arithmetic, logic, and shift unit. If you see the circuit, here is a multiplexer at the output end, and we have arithmetic circuit, okay, that performs, okay, here is an arithmetic circuit that performs arithmetic micro operations, and this logic circuit performs logic operations, okay, logic micro operations. And here shift micro operations are performed, shift right and shift left. And finally, we have a multiplexer that chooses one among these 4 operations. Okay, arithmetic micro operation or logic operation or shift right or shift left. So here let's see the registers used. This AI and BI, okay, AI and BI are the 2 content of the register. Okay, these are the inputs to the, these are the actual inputs to the, for performing arithmetic and logic functions. Okay, arithmetic and logic micro operations are going to be performed on bit AI and BI. This is one stage of arithmetic and logic shift unit. Okay, for performing arithmetic and logic operations on this single bit, okay, of two registers A and B, AI and BI, ith bit, okay, AI and BI. So AI and BI are the inputs. And here, if you see this S3 and S1, okay, these two are the selection lines. S2 and S3 are the selection lines that is connected to the multiplexer. Okay, so S2 and S3 are the lines connected to the multiplexer. And what is S1 and S0? Okay, the other two selection lines, S1 and S0, are the selection lines, okay, to control the operations of arithmetic circuit and logic circuit. Okay, these are connected to this is S1 and S0. And here, this is again S1 and S0. These are the selection input. To the arithmetic circuit and logic circuit. Okay, S1 and S0 are the selection inputs to the arithmetic and logic circuits. And S2 and S3 are the selection inputs to, okay, here this is S3 and S2 are the selection inputs to the multiplexers. AI and BI, 1 minute. Yes, AI and BI are the two inputs. And here there are two inputs given to the multiplexer AI minus 1 and AI plus 1. Okay, so AI minus 1 and AI plus 1 are the, okay, inputs for performing shift right and shift left operations. Okay, this AI minus 1 and AI plus 1 are the inputs for performing shift right and shift left operations. And there are two other inputs. One input CI and CI plus 1 is the output from the arithmetic and logic unit. Okay, so CI and CI plus 1 are the carry input for performing arithmetic operations, the two binary numbers, and the third number is the carry, right? The full adder uses to add the two binary numbers and the carry input. Okay, so CI is the carry input. CI plus 1 is the carry output. After performing addition, the carry output that need to be connected to the next circuit, arithmetic circuit. This is one stage. So I plus 1th circuit, see I plus 1, carry I plus 1 will be connected to the I plus 1th circuit, arithmetic circuit. Okay, so these are the carry in and carry out, okay, of the arithmetic circuit. And what are the other variables here? DI and EI. DI is the arithmetic output. Okay, output from the arithmetic circuit, and EI is the logic output. Okay, output from the logic circuit. Okay, this logic circuit performs logic operations, and this arithmetic circuit perform arithmetic operations. We have discussed around 7 or 8 arithmetic operations. So all those arithmetic operations are performed by this circuit. Okay, and let's finish this. FI. FI is the final output. Okay, if you see here, output from the multiplexer is Fi. Okay, So here AI and BI are the two inputs for performing arithmetic and logic operations, micro operations, and AI plus 1 and AI minus 1. Okay, AI minus 1 is for performing shift right operation. AI plus 1 is for performing shift left operation. And S0 and S1 are the two selection inputs to arithmetic and logic circuits. Okay, for selecting, why these lines are connected to arithmetic and logic circuits? Because there are many operations, many arithmetic operations. It may be A plus B, okay, or it may be performing A plus B complement, or A plus B complement plus 1. Okay, we saw when we learned about arithmetic micro operations. All those operations are done by this arithmetic and logic circuit. Okay, so one of the operation need to be selected and given as output, okay, in DI. So that's the reason we use these selection lines S1 and S0 here. And for logic operations, there are many, okay. Out of all those operations, one need to be selected and directed to output EI. So here S2 and S3, okay, if you see this S2 and S3, these are the selection lines given to the multiplexer. And this arithmetic and logic, arithmetic circuit performs arithmetic operations. DI is the output from arithmetic circuit. So one of the arithmetic operation, and EI is the output from logic circuit. Okay, one of the logic operation. Now the multiplexer has to select one of these inputs. What is 0? 0 is the arithmetic operation. Okay, that is the output of connected to arithmetic and logic circuit. Arithmetic circuit. Okay, so it is the arithmetic operation, okay, that is given as the output here. Okay, so that it performs arithmetic, and the one input to the multiplexer is the logic output. Okay, the logic operation that is selected by the logic circuit. And 2, okay, the input 2 to the multiplexer here is shift right operation, and input 3 is shift left operation. Okay, so this multiplexer finally, using the selection inputs S3 and S2, it has to select one among these inputs. 0, that is either it performs arithmetic operation. 1, it performs logic operation. 2, it performs shift right. Or 3 is shift left. Okay, it performs, finally, it directs one of these operation as output. So in Fi, okay, the output would be, okay, we get one of the operation done. And to, yes, if we take this arithmetic circuit, okay, this is the circuit that is, okay, replaced in that position. And here, this part, okay, what all the inputs to the arithmetic and arithmetic circuit, it is A0 and B0. Okay, so this part of the circuit. One minute. So let's draw that one stage of arithmetic circuit here. The input to the circuit is, here we have S1, S0. S1 and S0. And input is A0 and B0. Okay, this is connected to the parallel adder. Input is directly given to the parallel adder, and parallel adder takes the carry input. Okay, this is a carry input, and after addition we get carry out. Okay, this is mentioned in this circuit as Cin Ci plus 1 in our ALU circuit. And S0 and S1, here we have the multiplexer, 4x1 multiplexer. This is S1 and S0. And the other inputs to the multiplexer, 0th input is B. And the first input to the multiplexer is B complement, that is the input 1. And the other two inputs we have seen, okay, logic 0 and logic 1. Okay, so the negation, the complement of this logic 0. Okay, this is input 2, and input 3. Okay, input 0, 1, 2, and 3 of the multiplexer. And here output is Y, correct? And so the input to this parallel adder are AI, the first input. Here it is A naught, and this Y. Y is the input. Parallel adder adds A naught and Y. Okay, Y is the output from the multiplexer and the carry in. Okay, and it generates some output and carry output that is forwarded to the next parallel adder. So this is one stage of our arithmetic circuit. Okay, so here in ALU circuit, what does this mean? This one stage of arithmetic circuit is this. Okay, so using this, the operation is the circuit is you can imagine this, okay, in place of this arithmetic circuit. And here how the operations are performed. Okay, A naught is the first. What are the operations performed? That depends on S1 and S0, correct? If S0 and are 0, both are 0, the input, okay, multiplexer input that gets selected is B. Okay, it is 0. So the value output B, Y will be B. And the operation performed would be, this is B. So here A naught plus B naught, it's B naught. Okay, so what the parallel adder does, it adds A naught plus B naught, and here the carry input may be 1 or 0. So if we take 0, okay, the case 0, it is A naught plus B naught because carry input is 0. When carry input is 1 with the same S1 and S0, okay, the Y output is B because it is S0 and S1 are the same. This performs A naught plus B naught plus 1. Okay. Zero, 1. Okay, S1 and S0, 0 and 1. When it is 0, 1, the first input, okay, input 1 of the multiplexer is directed to output. That is B complement, correct? B naught complement. And the operation here, if carry is 0, the operation performed would be A naught plus B naught complement. And if carry is 1 here, the same selection inputs, the Y output is B naught. So here A naught plus B naught complement plus 1. Okay, this is subtraction. Okay, this way for all the selection inputs. Okay, the other two possibilities 0 and 1 1 for all the selection inputs, and with two carry input 0 or 1. Okay, the corresponding arithmetic operation gets selected, and that here this multiplexer select one of the operations. So let's write the function table for this ALU. The selection inputs here are S3, S2, S1, S0, and the carry input Cin to the arithmetic and logic circuits only. And yeah, the output is Fi. Okay, so here first let's take this arithmetic. It may be 0 and 0. Okay, Cn is 0 and 0 0 with Cn 1, and 0 1 with Cn 0, and 0 1 with carry 1, 1 0 with carry 0, 1 0 with carry 1, 1 1 with carry 0, and 1 1 with carry 1. So these all the different arithmetic operations, right? When 0 0, the operation performed, we saw that it is a plus b, correct? And 0 0 with carry in 1, it is a plus b plus 1. And 0 1 with carry 0, we have seen that the arithmetic operation performed is a plus b complement. With carry 1, it is a plus b complement plus 1. It is subtraction. Okay, and 1 0 with carry 0. Okay, you can recollect the operations the function table we wrote when we learned about arithmetic micro operations. 1 0 with carry input 0. Okay, the y input will be with S1 and S0, 1 and 0. Y input is, what is the y input? Somebody can tell me? It is logic 0, right? The third input to the multiplexer is logic 0. And with the so carry is 0 here, right? So it is A, means A plus 0 plus 0, it is A. Okay, the operation performed is transfer. Transfer the content of A to register F, maybe. And 1 0 with carry 1, that is A plus this operation plus 1. Okay, because carry in is 1, that is increment. Okay, the arithmetic operation performed is increment. And 1 1. Okay, when S1 and S0 are 1 and 1, with the carry 0, okay, y would be 1, that is the negation of 0. Okay, 0 input and 1, logic 0 and logic 1 are the last two inputs, so the last input is 1. So it is, when all the inputs are 1, as I said, it is the 2's complement of 1, so it is A performing A minus 1, decrement. Okay, and when the carry is 1, okay, A minus 1 plus 1, so it is A, again transfer of A. So these are all the arithmetic operations performed by this particular circuit, arithmetic circuit. And all these cases, if you see, this is the input, okay, get selected, and the selection input S3 and S0 will be 0. Okay, when S3 and S2, sorry, S3 and S2. Okay, when S3 and S2 are 0, the 0th input of the multiplexer, okay, will be selected. So one of these operations will be performed. All these cases, S3 and S2 are 0 for all arithmetic operations. And the next case with S3 and S2, 0 and 1. Okay, when it is 0 and 1, okay, the second case, the input gets selected. Okay, the multiplexer input that get directed to output is 1. Okay, what is 1? It is the logic output of the logic circuit. Okay, now we have to see the logic circuit. Okay, this is the circuit. Okay, that is that replaces the logic circuit in our ALU. So the operation performed here, the basic gates, okay, and gate, OR gate, and XOR and NOT gate are given. Okay, so the operations performed would be one of these operations. Here, the selection input 0 0. There is no carry for logic operation, right? Only for arithmetic operation, we take carry in and carry out. So here there is no carry. So we can, in the function table, we can denote this by using this cross. This means don't care. Okay, we call this a don't care condition. And the selection input 0 1 with no carry. Okay, here in our circuit, the first operation 0. Okay, when it is 0 0, the operation gets selected as XOR. Okay, the 0th one. And when it is 0 1, it is OR. Okay, so here it is XOR and this case it is OR, and 1 0 with no carry, it is and the last one is with 1 1 not. Okay, these are the logic operations performed by the circuit. Okay, so here this logic circuit perform one of these logic operations. The output EI will be one of these logic operations with the value of S3 and S2 as 0, 1, the second case. Okay, because when it is 0, 1, the input 1 to the multiplexer is selected, that is the logic output. Okay, logic operation. And the third operation, okay, here input 2 to the multiplexer is shift right. Okay, so here it is the value of S3 and S2 will be 1 and 0. Okay, in this case, okay, here we don't have a selection input also. This is a single operation, shift right. There is no selection inputs and no carry. Okay, the operation performed is shift right. Okay, here if you see the input given to the shift right operation is AI minus 1. Okay, so this is ith position, okay, in A. This is I minus 1. This is I plus 1. So when this is given and shift right operation is performed, the bit gets moved to ith position. Okay, so the operation performed is shift right. And next, when S3 and S2 are 1 and 1, with no selection here, it's a single operation, no carry, the operation performed is shift left. Okay, and the input is A I plus 1. Okay, the I plus 1th bit of A, and that is shifted left. Okay, it is moved to AI. Okay, so finally this Fi, the output Fi of the circuit would be one of these arithmetic operations. Okay, if S3 and S2 are the selection inputs to this multiplexer, S3 and S2 are 0 and 0. And one of these logic operations, if the selection lines, okay, selection inputs S3 and S2 are 0 and 1. And shift right operation, okay, output of the shift right, if the selection inputs S3 and S2 are 1 and 0, and shift left if it is, okay, if S3 and S2 are 1 and 1. Okay, this way this arithmetic logic and shift unit replaces, no, it combines all the arithmetic logic and shift micro operations. Okay, micro operations, okay, means the elementary or the basic operations. Okay, by combining these micro operations, we can perform, okay, we can implement a complex operation. Okay, any complex operations can be implemented, no, divided into small units. Okay, those are micro operations. Okay, so this circuit is used to perform these micro operations. So we'll start the next chapter in the next class. Okay, it is basic computer organization and design. Any doubts here? Let me check the attendance. Any doubts in this?